Have you ever heard of neutron stars? They are like the superheroes of the universe. These incredible objects are incredibly small but unbelievably dense. Imagine squeezing something as massive as our sun into a ball only about 12 miles across. That's how tightly packed a neutron star is. These cosmic giants are born from the fiery deaths of massive stars, much larger than our own sun. When these stars run out of fuel, they collapse under their own gravity, creating a spectacular explosion called a supernova. The core of the star, however, survives this cosmic cataclysm. It gets squeezed so tightly that the protons and electrons within its atoms merge, forming neutrons. And that's how a neutron star is born. Imagine a star much bigger than our sun, maybe 10 times bigger. For millions of years, this star shines brightly, fueled by nuclear fusion in its core, just like our own sun. But eventually, the star starts to run out of fuel. Without the outward pressure from fusion, the star's core begins to collapse under its own immense gravity. This collapse happens incredibly fast, in just a matter of seconds. The outer layers of the star are blasted outwards in a massive explosion that we call a supernova. At the center of this explosion, the core of the star remains, but it's no longer a normal core. The immense pressure from the supernova has squeezed it so tightly that the protons and electrons in the atoms are forced to combine, forming neutrons. This newly formed ball of neutrons is incredibly dense, and it spins rapidly, emitting beams of radiation from its poles. This, my friends, is a neutron star, a tiny, incredibly dense remnant of a once giant star. Neutron stars are not just incredibly dense, they also possess other mind-boggling properties. They have incredibly strong magnetic fields, trillions of times stronger than Earth's magnetic field. These fields can create powerful jets of radiation that shoot out from the poles of the neutron star, making them visible across vast distances. Because of their intense gravity, neutron stars can also warp time and space around them. Imagine a clock placed on the surface of a neutron star. Due to the strong gravity, this clock would tick much slower than a clock here on Earth. This effect, known as time dilation, is predicted by Einstein's theory of general relativity. Neutron stars can also spin incredibly fast, with some rotating hundreds of times per second. This rapid rotation is another consequence of the conservation of angular momentum during the star's collapse. A teaspoonful weighs a billion tons. Let's dive into the concept of density. Think about how a bowling ball feels heavy for its size. Now imagine a neutron star as a bowling ball compressed to the size of a city. If you could scoop up a teaspoonful of neutron star material, it would weigh billions of tons, heavier than Mount Everest. This incredible density is what makes neutron stars so intriguing to scientists. To give you an idea, imagine shrinking the Earth to the size of a neutron star. Our entire planet, with all its mountains, oceans, and people, would be compressed into a ball only about 12 miles across. That's smaller than most cities. New discoveries in the cosmic sea. Scientists are constantly making new discoveries about these cosmic powerhouses. Recently, astronomers using the James Webb Space Telescope observed a neutron star behaving very strangely. It was pulsing in a way that had never been seen before, suggesting the presence of unknown physical processes at work. This discovery has sent ripples of excitement through the astrophysics community, as it could provide new insights into the nature of matter under extreme conditions. It's a reminder that the universe is full of surprises, and neutron stars, despite their small size, still hold many secrets waiting to be unlocked. The study of neutron stars is crucial for our understanding of the evolution of stars and the fundamental laws of physics. They are like cosmic laboratories where we can observe matter under conditions that we could never replicate on Earth. From neutron stars to red giants. We've explored neutron stars, these tiny titans born from the death of massive stars. But what about stars that are even larger? What happens to them when they reach the end of their life cycle? Well, that's a tale for another episode. Let's just say it involves red supergiants, black holes, and perhaps even more mysterious objects lurking in the vastness of space. Please like and subscribe. Thank you.